introduction. So I'm Sven, and I will present our work on interval bound propagation. And actually, the previous work from MIT was a perfect introduction to that talk. So I hope it will also be enjoyable for you. This work is basically, actually, I'm sorry, because I need to mirror my screen, because otherwise I don't see the slide. So I want to thank all my collaborators at DeepMind, and I want to point out that this paper is available on arXiv, and we've also released the code open source at DeepMind/interval bound propagation. So I think everybody knows about the panda that wanted to be a gibbon. So I'll make the example a bit more concrete. Let's say we have trained a robust network on MNIST, and we want to classify that image of a 9. So there's no problem here. If we pass the nominal image to our network, it will be classified as a 9. And now we want to have a specification on that particular example. And the specification is that the output of our network should remain a 9 for all possible perturbation around that nominal image. And so if we have access to the internal weights of our model, we can actually use projected gradient descent to build an attack and try to find a counterexample to that specification. So here, with 10 random restarts, we're not able to find an adversarial perturbation that will actually misclassify the 9 for another class. However, if we run a true worst case attack, so that is, we run a MIP solver to find all possible, to try and go through all possible perturbations of that 9, we're actually able to find an image that will be misclassified as a 5. And so that really goes to show that you can't necessarily trust the attack to be the optimal attack. And so if you want to be future-proof, you need to have these verifiable models that can guarantee that some specification will hold. And so when it comes to verifying neural networks, there's been a lot of work about this. There's also even more work on adversarial robustness and training robust models empirically. However, when it comes to training provably robust models, there's really two approaches. The first one is the empirical approach. That's exemplified by the paper by Xiao, which actually takes advantage of the mixed integer program that you're going to build after training. And what it tries to do is reduce the number of ambiguous values in your network so that the training, the verification post-training becomes very easy. The second set of approach are the relaxation approach, one of which was exemplified in the previous talk. And really this list is non-exhaustive, but the idea here is to compute a differentiable upper bound on that adversarial specification, and if you can compute that adversarial upper bound quickly, and this upper bound is differentiable, you can actually use it for training. And so just to highlight like 4 of those, actually the 2 on the right side here, one is a previous work from DJ, which tries to build Lagrangian relaxation, and so it introduces a set of duals that can then be optimized within the training loop. And if we actually set the duals to 0, we end up going back to the subcase of interval bound propagation. The last paper here by Matthew from ETH is introduces like geometric abstractions to try and bound to try and find better convex relaxations. And one of the abstractions that they have in that paper is actually called box, and is exactly the equivalent of interval bound propagation as well. So actually, this is a good time to make quite a disclaimer about this presentation in this paper. So I'm not going to present a new formalism for interval bound propagation. What this paper does is just a thorough evaluation of interval bound propagation. It just demonstrates how you can achieve state-of-the-art verified accuracy on MNIST and CFAR using the simplest possible method, which is interval bound propagation. It only focuses on infinity non-bounded perturbation, and we also perform a fair evaluation with other methods using the complete MIP solver. So just a recap, a quick recap of the previous talk. So if we have a neural network, which is a set of operations denoted here by HK, and we have a linear specification, we want to verify that this specification is below 0 for all possible inputs within some adversarial polytope. And in the case of adversarial specification, we just want to check that the logits of other classes are bigger, are smaller than the logit of the true class. And we want to do this for all inputs within that L-infinity ball. And so really the problem becomes a problem of maximizing that linear specification and trying to find a counterexample to the specification that will yield a value bigger than 0, subject to the constraints of our neural network. And finding this counterexample is pretty hard. So you can of course use attacks like PGD, but that doesn't give any guarantee that you're going to find the worst case attack. And if PGD says you're robust, then of course, like, you don't know that you're actually robust against a stronger potential adversary. The other approach is to run the exhaustive search using MIPSolver, for example, but we know that this is not quite feasible during training because this is going to take quite a while. It is barely doable after training under certain circumstances and for fairly small networks. And so the idea behind interval bound propagation is to relax this optimization problem as fast as possible. So let's say we have a network that is this sequence of operation on the top, and we have an input and the corresponding adversarial polytope around that input denoted by this red square. As this square propagates through the network, this shape is going to become arbitrarily complex and concave. And what we really want to do is try and find a worst case violation of our linear specification in that, on that adversarial polytope. However, this is fairly hard, and so that's where relaxation methods come in. They try and find a convex hole around this, this adversarial polytope that is easier, for which it's easier to find the worst case violation. Interval bound propagation itself is quite simple. It just tries to put an axis-aligned box around around this adversarial polytope, and by doing so, you're going to lose a lot of the tightness properties. That is, at the last layer, you're going to be quite far off from the true violation of your adversarial polytope. But the hope is that if you use interval bound propagation during training, you can try and throw that violation into a loss, and you try to minimize it to bring it below 0. Then what's going to happen is that also the adversarial polytope that is within that box is going to move on one side of that specification boundary. And so in that case, you can actually certify that there is no possible attack that will be violating the specification. So there are a few tips and tricks that we highlight in the paper about making interval bound propagation work well. The first one is the elision of the last layer. So that means that since our last layer is actually a linear layer and our specification is linear itself, we can combine these two to make a new linear specification. So that roughly reduces the error rate, the verified error rate on MNIST by roughly 5% in relative terms. The second one is the loss. So typically, and what has been done in the ETH work is to use a hinge loss or a soft plus loss on that violation, because what you want to do is bring it below 0, and then once it's below 0, you're happy. However, if we realize that the violation on that convex polytope, so the axis-aligned polytope, actually also corresponds to worst-case logits, you can actually use these worst-case logits into a standard classification loss, like cross entropy. So that also helped us get a further improvement on the verified error rate. And finally, I think the most important thing to do is actually schedule and create a curriculum on that adversarial perturbation. So rather than starting to train your model using a very high epsilon, which creates this very loose bound using interval bound propagation, you're going to start it with 0, which would correspond to standard classification. And then as training goes on, you're going to increase it linearly until a target robustness value. And actually, we noticed that you should go slightly higher than the robustness you want in order to have good generalization of that robustness on the test set. Our evaluation setup is that we use different model sizes, and we train across a wide range of different perturbation radii on MNIST and CIFAR10. We compare with our own trained model using Wong et al.'s method, and we verify all these methods using the complete solver when possible. We also compare with values reported in the literature, mainly Xiao and also Wang. And the paper includes a lot more detail that I will skip for this presentation. So if we look at the state of the art on verified error rates on MNIST and CFAR, on the y-axis we have the verified error rate, so lower is better. And on the x-axis you have different perturbation radii. And so we can see that we can achieve fairly good robustness, at least on MNIST, with 0.1 perturbation. And then if we use IBP, we're actually able to significantly lower this verified upper error rate. And it's quite striking on MNIST. So on MNIST, we're almost 3 times better on this larger perturbation radii. And we're quite competitive on CFAR. So even a very simple method is able to get quite a good verified upper bound on the error rate. The glimpse of hope that I have is this where we do worse, actually. So we see that we do slightly worse on CFAR with the small perturbation radii, and that actually gives me hope that more complicated methods will hopefully be able to improve on other results of interval bound propagation here. Another question that comes up is the question of tightness, which has been alluded to by Aditi. So if again we plot the verified error rate as computed by the MIP solver post-training using the IBP models, and now we're using the same models and we verify only with interval bound propagation, we can actually get very tight. So that is in the sense that our verified error rate using IBP only is already very close to the value that we get using the complete solver. And that goes to show that when you train a model to be verifiable using IBP, you're going to have a model that is more easy to verify using IBP. And we've seen that in other works as well. When you train with Wong-et-al methods, then it's going to be more verifiable with that, and so on. So I'd like to conclude with mainly 3 questions. So the first one is, does IBP reduce the expressivity of our models? In the sense that if we force the model to be verifiable under this interval bound propagation strategy, are we losing in terms of expressivity of our models? Can we compensate for it by adding more capacity? The other one is, we know that IBP is going to be very loose at the beginning of training. So is tightness at the beginning of training important? And that seems to be exemplified by the fact that we need this curriculum. And so maybe methods that provide tighter bounds at the beginning of training can be used. Maybe they're more expensive, but then we can slowly relax into a more faster to optimize method. And finally, do we need to capture this relationship between hidden units? So the SDP approach that you've seen in the previous talk captures this relationship. IBP doesn't. Is it important to capture this relationship in order to unleash the further potential of verification? And finally, I want to point out that IBP is actually a very worthy baseline, and so if you're writing papers about verified training, please use IBP. And so if you have any questions, I can answer them now or at the poster session. Thank you.
Thanks a lot for this great talk. So actually, in the interest of time, since we're running a bit behind, and because we're going to have a poster session right now where this paper will be presented, we'll skip questions and